Hello there, spacewalkers, and welcome to our study on the space and Mars settlement water life cycle and H2O production, infrastructure treatment, and storage. Publishing for and with the Ascend 2022 conference on behalf of Multi-Planet University. So over the past few years, we've really conducted this deep dive into a 25-page literature review and analysis on the design systems and materials of a water life cycle and a settlement beyond Earth, primarily focused on Mars, but with implications for Luna, Venus, and beyond. And so we're really highlighting some of the waste management systems at McMurdo Station, ISS, and the native sources on Mars, and various H2O production methods and storage systems, and some exciting nanotechnology and methods to help recover more water, and then also analyze the quality, the data, and demand estimates, and to really enable high quality drinking water for life beyond Earth. And so here are some of the primary native sources of H2O on Mars. There's this underground lake reservoirs, and we know that there's a lot of ice locked up in the polar caps as well, and there have been consistent measurements of liquid brine water and hydrated minerals in the upper surface of the regolith, around 0.5 to 10% by weight. And to really help inform the design of the systems, we can reference the water management in extreme environments in McMurdo Station and Russia and beyond. And so there's a population of 1,200 people per summer, and they primarily use rodwells since 1995, produce 208,000 liters of clean water per day with a desalination plant and wastewater treatment plant. So the untreated seawater is used to flush the toilets, and this approach really recovers and saves more energy and costs as a high water analog. And here with this low water analog on the ISS, there's we've made a lot of developments over the past 30 or so years, and so water is primarily produced from imported water and electrolysis and fuel cells, and through this water recovery system and unit here, outlined here in the diagram, with the water processing assembly, where almost every H2O source, including the sweat, vapor, wastewater, urine, and everything's recycled. And so this WPA produces 132.5 liters, and this has significantly reduced the water delivery to the ISS by over 3,700 liters per year, which results in almost $10 million in savings. And so we've also outlined the wastewater treatment subsystems here in this diagram, with the urine treatment and shower water treatment. Okay, so we're coming back to Mars and really evaluating the hydrological cycle on Mars. And so we know that substantial amounts of water is released in the atmosphere, and it's interesting that the relative humidity can rise 80 to 100% at night as well. And so if the goal is to be closer to the mid-latitude, there's the candidate landing sites around 35 to 45 degrees north. And so we know that the perchlorates also reduce the freezing point of water, which will aid in mining and extraction efforts, and really following the recurring slope linea as well in Valles Marineris. And so, there used to be this global reservoir and this massive ocean on Mars then, and we believe most of it Most of the water loss occurred around 3.7 to 4.1 billion years ago, but then a lot of data also suggests that the 30 to 99% of that water is still there, locked up below the surface, in the equivalent of half of Earth's Atlantic Ocean, primarily in the northern hemisphere. And so detect this water with GPR and the low frequency electromagnetic exploration outlined here, and with this really wonderful slide deck here on GPR and electromagnetics, and then also how aircraft-based systems can detect water several hundred meters to depth, in depth, in addition to aiding relevant ground system measurements. And so here's a study from NASA Ames outlining the water supply and treatment system in transit to Mars, and the 20 key subsystems here: the fuel cell and stored water to supply water on the inbound and outbound journey. And so they've also outlined some of the water system requirements for a Mars base, and we've adapted some of these estimates for a Mars and Moon base here, with the kilogram per crew member per day, water consumption around 4.17 kilograms per day, scaled up to a 18-man and 36-man crew, with in addition to accounting for the wastewater demands. And so it's interesting because around 88% of the survival water can be provided from fully hydrated food, and also from the human food and metabolism. And so here's some consumables and estimates from the NASA DRA reference mission, with oxygen, methane, nitrogen. With a slide here on the water production methods on Mars, including the atmospheric WAVAR unit for vapor extraction, solid oxide fuel cells, and PEM fuel cells, which can easily produce over 3 kilograms of H2O per day, with imported methane and then in situ CO2, and as well as a rodwell mining process and brine electrolyzers, and this concept of thermal mining and these passive methods of water extraction with the silica aerogels. And so we can balance all this with the settlement water demands and estimates, as the settlement would expand in relation with these civic water demands here, and some of the algae biofuel water demand estimates here, with humans consuming around 3 kilograms of water per day. A slide on the water cycle and controlled drainage for soils and agriculture. There's a study evaluating that the aeroponic systems had over 8,000 water% efficiency, and the nitrogen and phosphorus in the lettuce was 64% higher in the aeroponics, with the drainage water management systems and also boom watering systems for greenhouses. With a slide here on the water piping and distribution with PEX, PEX for pipes, and FRPs as well. And a slide here on the nanocoatings for water infrastructure, with these coatings to reduce H2O to flush toilet by up to 90%, and other methods and technologies for the cracks and molds and damaged piping, and coatings for reapplied technology and hydrophobicity of surfaces. So here's a slide on the cryogenic liquid storage tanks with high density polyethylene and methods to manufacture the HDPE in situ for mass and size savings. And so it's really this water quality monitoring smart data system, where all of this data is coming together with a lot of sensors, leak detectors, valves, pump rates, leaks, and a lot more. And so that we also know that the radiolysis of water produces these reactive OH species and other particles that should be measured, filtered, and removed accordingly for consumption. And so this approach with the silica aerogels and heating greenhouses becomes very attractive too. The last slide is that, it gets really interesting when we start thinking about Europa, Callisto, Titan, and Ganymede, with much more significant water fraction than even here on Earth. So thank you for your time, Ad astra.